Hello students, welcome to this module in which I'm going to start introducing the basics of how to perform a linear stability analysis of the Navier-Stokes equations. Now by way of example, what I'm going to do is I'm going to consider a simple laminar flow that is called the combined Couette-Poiseuille flow in a rectangular channel. Okay. Imagine you have two very wide plates, okay, and okay, these are two very wide plates, and this is the gap in which fluid is flowing. Let's say the thickness of this gap is B, right, and this length is very large compared to B, and the width into the screen is also very large compared to B. Okay, and fluid is flowing in this direction, and fluid is flowing due to two reasons. One is that the top plate itself moves with a velocity u wall, that is the Couette component, and of course we'll assume that there is a pressure difference delta P across the two ends of the channel, so that is the Poiseuille part. Okay, that's why this is called the combined Couette-Poiseuille flow. Now in the limit when W is large compared to B, we can neglect variations in just for the sake of concreteness. Let's put a coordinate axis. This is X, the flow direction, Y is the direction into the board, and Z is the direction perpendicular to the wall in the Y direction. Such an assumption is called a two-dimensional flow approximation. In reality, there will be side walls at the two, at this side and at this side. So there will be a small region of order thickness of order B, wherein there will be some effect of the wall and the flow will not be two-dimensional, but in the majority of the channel the flow will be two-dimensional. So within the 2D flow approximation, what we are going to look at is simply these two plates. This is X, this is Z, and into the board is Y. The top is moving with U wall, and because we are not interested in this direction, we are not going to consider it in our analysis because we are going to assume only the 2D flow, right? And this, let's call this Z is equal to 0, let's call this Z is equal to B, and this is the length L of the channel, and there is a pressure drop of magnitude delta P across the two ends. Okay, and the velocity profile will look like a combination of the plane Couette flow, which is like this, plus the plane Poiseuille flow, which is like this, the parabolic velocity profile. If I add the two, you get this. I can add the two because for the assumptions that we are going to use in the laminar flow, it's fully developed, two-dimensional, steady, etc., unidirectional. Then the Navier-Stokes equations will become linear, and when things are linear, you can superpose the solutions for two different kinds of driving of the flow. Okay, now, so the base state, the laminar flow, whose stability is of interest, is called the base state. Okay, this is the base state is the laminar flow velocity profile whose stability is of interest. Okay, so the base state is Vx is some velocity profile Vx bar of z, Vy is 0, Vz is 0. Okay, now the x momentum equation in the base state will be given by minus dp dx plus mu d squared Vx by dz squared is 0. Okay, and Vx is 0 at z is equal to 0, and Vx is u wall at z is equal to b. And since the flow is in the x direction, positive x direction, dp dx has to be negative, so I'll call dp dx as minus delta p by L, okay, where delta p is p entrance minus p exit. Okay, if I substitute this, I'll get d squared Vx by dz squared. The over bars denote that it's a laminar flow. Okay, then you have this mu plus delta p by L is 0. Okay, now if I take this to the other side, okay, now if I solve this, I'll get minus delta p by 2 mu L. I integrate this twice with respect to z, z squared plus c1z plus c2. Okay, now use these two BCs to fix the two constants. Then finally one ends up with Vx is equal to delta p by 2 mu L times zb minus z squared plus u wall z by b. This is the Poiseuille part of the velocity profile. This is the Couette part. Okay, now so this is the velocity profile whose stability is of interest. Now in stability analysis, in linear stability analysis of Navier-Stokes equations, much similar to what we did for 1D systems that I introduced a few modules earlier, what you do is the total velocity, which is a function of x, y, z and time, is written as the sum of laminar or base state velocity profile, which is a function only of z, plus a deviation or fluctuation or perturbation, which is denoted as primes, and this is in general a function of all the coordinate directions and time. Okay, this is the base state whose stability is of interest, and these are the fluctuations or perturbations. Perturbations are denoted by this prime symbol or prime superscript. Okay, now what about Vy? I'll, for the sake of saving time while writing, I'm going to write the total. This is the total velocity. Total fluid x component of the fluid velocity is the base state plus fluctuation. Similarly, the y velocity also has base state, which is 0 plus fluctuation, and the z velocity also has base state, which is 0 plus fluctuation, and the pressure, the total pressure, is written as the base state pressure, which drives the laminar flow, plus p prime. Okay, now so this p bar is the p that we just wrote as minus delta p by L. Now first let's look at the continuity equation. For an incompressible flow, this is simply del dot v is 0. This is nothing but partial Vx by partial x plus partial Vy by partial y plus partial Vz by partial z is 0. Now I substitute these uh, for expressions for the total velocity Vx, Vy and Vz out here in terms of the base state velocity and fluctuations, right? So you will get partial Vx bar by partial x, Vy bar plus partial Vy prime by partial y plus partial Vz bar by partial z. Okay, now there are two ways to argue what I'm going to do now. The flow is fully developed. This is 0. It's unidirectional. This is 0 in the base state. This is 0. So that means that you are left with partial Vx prime by partial x plus partial Vy prime by partial y plus partial Vz prime by partial z is 0, or del dot V prime is 0. Because del dot V0 is a linear equation, it merely splits into del dot V bar plus del dot V prime 0, but then this is 0 anyway in the base state, so that means that del dot V prime is 0. All we are finding out is that the fluctuational velocity field is also incompressible, just like the base state velocity field and the total velocity field. Okay, now let's look at the x momentum equation and how it can be linearized. Now the x momentum equation for the Navier-Stokes equation is denoted or is given by rho partial Vx partial t plus Vx partial Vx by partial x plus Vy partial Vx by partial y plus Vz by partial z is, I'm writing the total in terms of the total velocities and pressures, right, plus Vx. Now if you know from earlier courses on partial differentials and so on, this is called the Laplacian operator, which is partial squared by partial x squared. This is called the Laplacian. Okay, all right, now let's now substitute Vx and so on, okay, out here. Now I'll get rho partial Vx bar by partial t plus partial Vx prime by partial t. Okay, now out similarly for the other variables, I'll have Vx bar Vx by partial x plus Vx bar Vx prime by partial x plus Vx prime Vx bar by partial x plus Vx prime by partial x. So I'm just writing this particular term now for the moment. Okay, this entire term is this. Okay, now let's see what terms are important and what terms aren't. Now the flow is fully developed in the base state, so this is 0. Okay, now what about the second term? This term is non-zero because it's a product of the base state velocity times the derivative of the perturbation velocity in the x direction. Now in the linear stability analysis, first of all, before I do that, the base state is steady, so this is 0. So this will stay because it's a product of base state velocity times a fluctuational quantity, which is non-zero. Now let's look at the third term. Here the base state is fully developed, so this is 0, so the third term will not contribute. Now the fourth term is very, very important. It is not 0 identically, but it is non-linear. It's a product of velocity and its derivative, so these are expected to be very, very small for small magnitudes of the perturbations. Okay, So for Vx small compared to 1, Vx is squared is much less than Vx prime and so on. Okay, the magnitude of square of the same when the quantity is very small compared to 1 is much smaller than the quantity itself. Right, so now let's proceed further. Plus, similarly, let's do for Vy. Let's do it for Z also. Sorry, this should be X. Okay. Um, okay. Now we'll have Vz. We're expanding this term. We have Vz prime okay. This is all that is there in the left side of the Navier-Stokes equation. Okay. Now let's again look at terms. Vy is 0 in the base state. Okay, same here. Now, although Vx is non-zero in the base state, it is not varying in the direction into the board. So this is 0. Okay. Now, this is non-linear. So although it's not 0, it is neglected. Okay. Now let's look at this term. There is there is no Vz in the base state, and again same here. Now this term is important. Partial Vx bar by partial Z is non-zero, so this will survive, whereas the final term is non-linear. This will be 0. Okay, so this is all that is there in the left side. The right side you have minus dp dx plus partial p prime by partial x, plus, because the Laplacian is a linear operator, we can write del squared v as del squared vx as del squared vx bar plus del squared vx prime. Okay, now let's focus on the right side for the moment. This is minus by partial x. Let's write this a bit later. Let's take this term. This is nothing but partial squared by partial x squared plus partial squared by partial y squared plus partial squared by partial z squared of Vx, and then you have there is a minus sign here. Then you again have minus partial p prime by partial x plus del squared Vx prime. Now in the base state velocity is independent of x, independent of y. Now this term partial squared Vx bar by partial z squared will precisely balance minus the pressure gradient of the base state, because that's what gave rise to the Poiseuille component. Okay, so this and this will cancel out. They two will cancel identically. This is called cancellation of the base state. Okay, ultimately leaving you only this. Okay, now after all this, let us try and simplify. or write down whatever we are left with after linearization. So we'll say after linearization of the x momentum equation, what you're left with is rho plus is minus by partial x plus del square Vx prime. So if you look at this equation, you'll have two terms that involve a product of the base state quantity and the fluctuational quantity. Okay. Now these are called the coupling terms that couple base state and fluctuations. Because if these terms were not there, there is no way that the base state and the fluctuations could talk to each other, and it is important for this coupling in order for the flow to be unstable. Okay, so these play a very, very important role. Similarly, the other, this is the x momentum, the y momentum, okay, is given by rho. You should try this at home, plus Vx bar partial Vy prime by partial x is minus partial P prime by partial y plus del squared Vy prime. Then the z momentum is nothing but minus partial P prime by partial z plus, I'm sorry, I should have kept mu out here. Let me correct this typo elsewhere as well. This is mu, okay, mu, okay. Okay. So now what we are left with is boundary conditions. The boundary conditions are that at at z is equal to 0, Vx is 0, Vy is 0, Vz is 0. We should write this as Vx bar plus Vx prime as 0, and so on, right? And you will find that because the bottom plate is stationary, it's not moving, so Vx bar is 0, so Vx prime is 0. Similarly, Vy bar is 0, sorry, Vy prime is 0, Vz prime is 0. This is for the bottom plate. But the top plate is moving with a velocity top wall, u wall, and so z is equal to b. What you will have is you'll have Vx bar plus Vx prime is equal to b. But if you notice, Vx bar is already equal to b at the top plate. Okay, so Vx bar is b. This is the base state no slip condition. So this b will cancel with this b to give rise to, again, Vx prime is 0, Vy prime is 0 at z is equal to b. Okay. Now, therefore, we now have three linear partial differential equations. Three linear, or you should say linearized PDEs. Okay, they are coupled. Okay, and we have homogeneous boundary conditions plus homogeneous BCs. Finally, you need to supply them with initial conditions. What is the at time t equal to 0? What is Vx prime, Vy prime, Vz prime? If you are able to specify this, then we will be able to solve this set of linear differential equations. Okay, so how we go about solving this, or how do we really solve this at all? These are matters that I'm going to discuss in the next module. Thank you.